Thank you all for joining us in this session. Today, inshallah, Mr. Bruno Ribet will be giving us a session about the diffraction imaging and fracture characterization for asset optimization. But prior to the session, let me just give you a brief about Mr. Bruno's journey in geophysics. So, Dr. Bruno, he's a subsurface science and engineering solution advisor in AspenTech. He holds a PhD in geophysics from the Institut de Physique du Globe from Paris University. He leads the interpretation and reservoir characterization customer-related activities at AspenTech, and his main role is to advise on developing workflows that take full advantage of the AspenTech SSE suite of geophysical and geological solutions to optimize asset performance. Also, he has over 30 years of experience in the upstream oil and gas industry. Mr. Bruno, kindly be informed that the session, inshallah, will be recorded. And starting now, the floor is all yours.
Okay. Thank you very much. Good afternoon, everyone. So I'm just starting my camera for you to just initiate the presentation. I will turn it off to avoid any issue. But by doing that, I would like, first of all, to thank the EAGE local chapter Kuwait for having me here, okay, to present about, diffraction imaging and factor characterization as an expert. So let's turn it off and I will start my talk. Obviously, the presentation is about diffraction imaging and factor characterization, but I would say the goal is for asset optimization, which means that effectively I will not present it with the point of view of a diffraction imaging geophysicist. I will present this from the perspective of a seismic interpretation, integration. Okay, what do we want to achieve through the use of, I would say, this kind of technique? What do we want to achieve by integrating various geophysical data? Obviously, we want to decrease the uncertainty. We want to increase the understanding of the reservoir from the seismic image. And that's very important, is exactly what I want to discuss today, is to increase our understanding of the reservoir from, I would say, a seismic perspective. So so the presentation the outline will be about just a short definition of what I understand about diffraction imaging, about effectively factor characterization. We will see where we can, I would say, get our results from. So I will talk about the method, the solution we are proposing, which is not a new one, but I think it's very interesting to come back on that and the reason why we should apply for such a method. We will talk about diffraction imaging. We will talk about azimuthal dependent analysis of residual velocity, VVAC, or amplitude, AVAG, and we will go to the conclusion. So when we talk about diffraction, it's a dictionary definition, I would say, okay? It refers to the spatial distribution of the intensity of the seismic wave resulting from the presence, okay, in the subsurface of a fracture, cavity, or cave, or any point diffractor that we can associate with heterogeneities in the subsurface. Okay, so, but when we talk more specifically about diffraction, the objective is really to reveal the low energy event. And the reason why is that because when we stack the data, these low energy events will disappear. And we want to make sure we can extract this information, and we want to make sure that it adds value to the work that we are doing when we interpret effectively, the architecture, for example, of the reservoir. And when we talk about diffraction, we also mix a little bit. So I would like to make sure that we understand the same terms. Okay, specular and diffraction imaging for me corresponds to the separation between continuous, so which is associated to specular, the high energy. Okay, it could be large faults, for example. It could be with large throat. Okay, it could be reflectors and discontinuous subsurface. Okay, and stratigraphic elements. So this is what about diffraction. When we talk about factor characterization, we talk about seismic anisotropy. And obviously, it's associated with the dependence of the seismic velocity with the direction. So we will talk in this case about azimutally dependent analysis of residual velocity or amplitude, VVAZ or AVAZ. And typically, we associate those azimuthal variations, okay, in specific layer. And those specific layer are mostly associated with the type of lithology that is, carbonate, tight sand, or shells, for example. So, and obviously, those particular layers are of high interest. We also assume that the fractures are oriented in a preferred direction, azimuthal anisotropy. But the main point here is not only talking about diffraction and I would say, factor characterization. It's also to mention about the method that we want to apply. And so to reconstruct, and optimize the full azimut, perspective that will allow us, to characterize effectively the diffraction and the factor characterization. So we want to recover of in situ azimuth of two types, reflectivity and directivity. We will understand better what it's about, but reflectivity, alpha opening angle, and azimuth, effectively. So where we will be able to study the variations of seismic velocities and amplitude versus the azimuth and angle, and directivity, is about the structure. It could be, a seismic dip meter. So we will understand effectively the dip, and the azimuth of the dip to be able to associate this to diffraction imaging and to separate specular from diffracted energy. And this is really, because we want to, to map, surface, the recorded data points, to the subsurface, to have the true position, geologic position of each point in the depth domain, each image point in the depth domain. And by analyzing this, by creating this type of data, we will get out of this method reflectivity and directivity image gathers. You can start to see how it looks, for example, for reflectivity gathers. We will see more examples here. And we can create an extended understanding of the subsurface with the analysis of this image gathers. So the solution, the method, is not new. We have already applied that extensively on a certain number of field. I would say we have a global exposure of applying this technique. This is the local angle domain decomposition to provide a pathway for recovering high resolution image from the subsurface, and it has been developed by Zikoren and Igor Haab. So what is this, seismic imaging in the local angle domain? What is the goal finally? So the goal is to build an image of the subsurface from recorded field data. But what we want to do is to reposition this data into their true geological position in the subsurface. So we want to make sure that effectively, we will have through location of each point, each image point in the depth domain. So the method that we are applying is from each point, the factor one-way ray tracing operator is applied for, I would say, for all angle, all azimuth, all dip, all azimuth of the dip. And the Ribet are built, so they are going to simulate effectively the reflected and the scattered events, but we also organize that, for separation, for the best separation between specular and diffracted energy. So if we have here, I would say this is the recorded data for each point in the depth domain in the subsurface. We are defining by 4 angles here, the opening azimuth and the half opening angle, which corresponds to the reflectivity image data. So this is exactly what we have. And we will generate the angle azimuth image gathers here. And the second pair of angle is about the dip and azimuth of the dip. So we are retrieving finally the dip angle relation, and we are building a dip angle image gathers. So finally, the outcome of this method for us, also as a seismic interpreter, is a set of 2 image gathers. First of all, the reflectivity gather, and second, the directivity gathers. And just to prove the importance here, I have just plotted, for example, here, I would say the azimuth. So we understand this is the full azimuth, for example, here, So, and we have here, for example, in the 3D view, it's, I would say reflectivity gathers, where we may understand that, we will see a synthetic example a little bit later during the presentation, but we will see some variation of the amplitude and velocities, against the azimuth. We can observe here. And for the directivity gathers, which is different, and we will also try to understand that later, we have also a full azimuth information. And this is how it looks like when we separate, for example, specular from diffracted energy. Here we have the maximum of energy, and we have the associated dip. So the axis from the center to the border here, is the dip, and not the angle as this is here. So from this full azimuth imaging in the local angle domain, this full weight field decomposition, what we want to do, we want to apply, alternative, it's exactly that, imaging technology to recover subsurface geological features that are not observed in legacy seismic data. When I say legacy seismic data, and this is effectively something interesting, and we will see an example later in the presentation. What can we retrieve? And I'm not talking about just the seismic amplitude volume that come from a previous depth migration. It's not that. I'm talking about effectively the legacy acquisition. Can we get more information from the legacy acquisition? Can we extract something that will help us to understand better, for example, the subsurface we are working on. We will see one example. But of course, I'll say we work full azimuth. So it's very important to understand that we maintain this approach along the process, along the workflow, when we work VVAZ, when we work AVAZ. So we take advantage, for example, of the full azimuth data. So which means that we will update more precisely the velocity model, because it will effectively take into account the anisotropy model. It will take the anisotropy model that we can extract from the full azimuth data. So we can plan and steer better the well, because of that. From those image giver, we will generate effectively, I would say, different types of image. And that's very important. Now I have access as a seismic interpreter to the reflectivity image gatherers. I have also access to the directivity image gatherers. Okay, what can I build? I can, of course, okay, stack everything. So which means that I will take into account, okay, all the angles and azimuth. Or I can separate by energy. I can say, okay, for example, I will maintain the specular energy. I will remove the diffracted energy, which means that, for example, I will be able to propagate, to interpret more easily. I will improve the signal noise ratio and even the folds, okay, the large folds. That's the purpose of the specular energy. And I will be able, from this specular energy, to create, okay, more structural attributes with a cleaner image, less noisy image. But I can also separate by and get the diffracted energy. Okay, so the low energy. So we have, for example, and we had an example, we will see some of them, but fractures, okay, mega cracks or cave, for example, if we talk about karst, okay, or if we talk faults with small throw, for example, okay, at the reservoir level, we will see some examples here. So we can use the full azimuth reflectivity gatherers suitable for fracture intensity and orientation here, VVAZ and AVAZ. How can we analyze, okay, along those reflectivity gatherers, okay, the oscillations that we may associate to the residual move out, and we will see that. Or can we look for amplitude variations that would indicate, for example, okay, which azimuth and which amplitude are associated? And are they associated to effectively, okay, a higher fracture intensity? Use fracture full azimuth directivity gatherers suitable for diffraction imaging, integration and calibration in an interpretation workflow. So first, okay, let's go to a usage, a view, an analysis of what I called an alternative image creation from full azimuth data. And it will be directly associated to the directivity image gatherers that we saw. And as you can see here, okay, the image that I am obtaining here, this is just an example, okay, is a stack that we are creating from the directivity gatherers. If you remember, this directivity gatherers, okay, image gatherers, is depending on the dip and the azimuth of the dip, okay? So if we look to the gatherers that we have associated to this image at that location, for example, it looks like, okay, this information. So this is obviously a little bit different to what we are used to work with. But what we need to understand is finally that I would say the geometry of the subsurface should define dictate a characteristic deep angle pattern. And as we see, for example, we see some events here, okay? We see some relation here. We see some event here. We need to remember that, okay, it's deep dependent on the x-axis and it's full azimuth. So for example, here, if I try to understand the relation between a reflector and here, okay, the characteristics on the pattern on the directivity gatherers, this is what we observe. We can go more deeply into this explanation. This is not the purpose, I would say, here of this technical talk. We have a fault. So the fault should be at, I would say, the same azimuth, at the same depth. So when we observe a pattern that, okay, exhibit a specific signature at a certain azimuth, okay, at a certain depth, we may associate to, to a fault. A pinch out, for example, it's another type of signature, which means that by understanding the characteristic, the different patterns that we can associate to each subsurface features, okay, we can confirm, for example, about, I would say, the fracture reservoir, the confirmation of fault presence, okay, the natural fracture corridor. We can optimize certainly the well placement, how close to the fault, drilling optimization, geohazard, for example. So we will understand better about the architecture of the reservoir and the compartmentalization. So a few examples here, but to discuss about. Here, this is a carbonate reservoir. This is the top reservoir. This is, we have generated, I would say, from the directivity gathers, we have separated specular from diffracted. We have the specular here. We can see very easily some major event here, some major fault here, but it's very difficult effectively to get a less accurate, a less sharp, a more sharp image. It's quite fuzzy here. And here, this is the diffracted energy. So we can see the combination of large faults, for example, here at the reservoir level. We can see also the mega cracks, But as we said, any point diffractor will have an impact on the directivity image gather and the image that we can create when we separate specular from diffracted, So we may have some, I would say, noise, some random noise, some organized noise. So I'm just saying that this is also the second step in the workflow would be to clean this information and to apply for some techniques like a structural guided tensor filter, apply using the specular on this one to filter this noise and get only the real image of the discontinuities we have in the subsurface. Another example here, this is also very interesting. This is the Eagle Ford, USA, onshore, shell, perfect. And what we have here, it's the specular image. This is the projection of the horizons area that we can see. This is the high amplitude events that we have propagated. And this is the major fault that we see. We can associate a very, I would say, easy pattern, easy fault network, but this is the diffracted image that we have obtained. And this diffracted image, what we did is applied not for the separation between, I would say, specular and diffracted energy, but we have applied for a structural mute because the gathers, depend on the dip. So if we say, for example, this is a flat structure, if I will remove every dip which is below, I don't know, 15 degrees, and take into account all azimuth to rebuild my image. This is the image that we have more complex, but we have effectively something which is more close to the reality we have associated to the reservoir. And that's another example here. This is the Barnett shell. This is the full stack. So we can see effectively the karst very easily. We can see the fault plane here, but can we get a more sharp image? We did the same. We did also a structural dip mute, so which means that it's a flat structure also. We have removed everything which was in this case, below 15 degrees, above 30 degrees, we took all the 0 to 360 degrees azimuth, and we created this image. So rather than starting from this image, as an interpreter, I will start to understand the delineation, precise delineation of the karst here, because of course for this example, and we know it, the lower Barnett shells is lying over an aquifer, the Ellenberger Formation, and those karst are effectively acting as intrusion from the Ellenberger Formation. We need to avoid those karst in this case. So we can see the level of details that we have in the definition of those circular features that are part of the lower barnett shell. An example of tight sand also, it's an onshore, it's from Abu Dhabi, okay, so low layer sands with some thicker dunes of no more than 100 meters, main fault with numerous small scale faults. I'm looking at this image mainly. This is what I'm interested in, the comparison between the two. So it's an image, a depth slice here, extracted from the legacy data that the interpreter has used for, understanding the reservoir. Okay, but of course, okay, the final response, the final judgment will be with the reservoir, the reservoir engineering and the drilling engineering also, because maybe effectively they will not observe the same production rate at different wells, okay, the same pressure. They need to understand that we add a fault here. So and you can see this is an overlay. It's light, but I hope you can see it. Here we have the diffraction, okay, image on the top of the legacy image, and we can see effectively, okay, some more faults here. Okay, a more thin description of the fault. They are more pronounced here. They are even appearing, and here also completely described. So which means that now we can build on the top of that. We can add the fault. We can improve the structural model that we will use for describing the properties of the reservoir and the simulation part here. I will jump effectively. Okay, I'm not only presenting depending on what you are working with, and what is the context, the geological context in Kuwait, but I think this one was interesting to prove the concept because it explained clearly what we intend to do when we talk about diffraction. This is fracture basement, this is onshore, this is Serbia here, and mainly from Serbia, they are producing from basement. So we need to understand, okay, very clearly the fracture zone, and it's very complex, obviously, okay, when we talk about fracture basement. So we need a more, I would say, accurate, okay, definition of the fault and fracture. We need to have a better image from which I can calculate effectively some attributes here. So this is exactly what is this example about. Okay, on the left, this is the legacy image. Okay, so that's all. We have already a good image. It's not the point here. We have the continuity, the basement here. This is clear. We have some events here. We have above, effectively in the overburden, we have good continuity of the sediment, and this is the new image we have obtained from this method. So we can see that we have less noise in the overburden part here. We have more continuity. We have increased the continuity of the seismic reflection. But the most important part is within the basement, where we have a cleaner, more continuous or discontinuous events. So we may have the possibility to reposition clearly, okay, differently here. Okay, you can note, for example, here for this event here. Okay, for this event here, it's changing its shape. So we have finally a better real image of the subsurface. And the idea was to compare the two images, because maybe, for example, we would be questioned about the amplitude spectrum. So we get a higher, okay, for the higher frequencies here. If we talk about frequencies or wave number, about the vertical resolution. So we have a better vertical resolution, but it's really, I would say, conformable to what was existing before, which is good, okay? And we have improved the signal to noise ratio quite drastically. So we start from this image, okay? And if we separate, for example, if we talk about interpretation here, this is what we had from the previous depth migration. So it was interpreted, for example, mainly east-west, okay? north-south, for example, with some trend, okay, that are a little bit different, but it was, okay, it was the interpretation. So it was on that. This is the projection of the fault polygons on the top of the reservoir. And by separating, okay, using this method on the directivity gathers, by separating by energy, specular and diffracted energy, this is the results, okay. This is, for example, an extraction on the top of the reservoir of the diffracted energy. And of course, we are looking for faults. Okay, we are looking to validate what we have here. We are looking for eventually improving our structural interpretation. And in this case, okay, it was completely different of what was observed until now and interpreted until now. Okay, so that was important, and it has been effectively refined or modified, and a new fault network has been designed, and obviously, okay, new wells have been drilled, and you have the story here: 2 wells that found oil, and 1 well effectively, okay, found water, but the reservoir. But what was important thing is that we move from one structural interpretation as it is shown here in the background to a new one, which is respecting what we observe, okay, on this full image directivity gathers by separating specular from, directivity. This is what I was talking about before from a legacy acquisition. This is the North Sea, but this is also to show, okay, what we can extract. Azimuth and angles, okay, deep in this case, are not sensitive to acquisition geometry. So we can generate effectively the directivity image gathers the same way we would do it for the full azimuth. We cannot generate the reflectivity gathers because here we would need effectively a full azimuth acquisition. But here we have the full stack. So we stack effectively the directivity image gathers for all dips and angle. Here we have the diffracted. We separate specular from diffracted energy. We see some effectively discontinuities. We see some organized noise. This is the filtered. I have used in this case a 3D mute. Okay, so I have separated by, I would say, deep, and mainly not deep here in this case, but azimuth. So I said, for example, what if, I'm selecting between that azimuth and that azimuth, I'm creating this image. And obviously, if I select, for a different azimuth sector, I would say, range, I will illuminate better. And this is the current cube now that I have created on this full stack, and I can see that they are perfectly correlated, and I can enhance better effectively some of the discontinuities that I have. So this is an example, of what we can do when we have effectively, I would say, a legacy data. Pre-salt, just very quickly, this is from Brazil, from Petrobras. It has been presented the same way. We have applied, this is the full stack from the directivity gathers. Can we retrieve image below the salt where, the seismic is effectively less high resolution? And this is the structural dip that we can, correlate with a semblance, a coherence cube. So this is the coherence cube. This is effectively the structural mute that we have applied on this image gathers. So, we have a better definition of those circular feature. We have now a clear definition of the faults here. So a clear definition of the faults here. So, for example, here, this event, which is appearing and continuing here. So now we can improve, the structural model. In another example from Kuwait, and we talk about the same. I can, of course, I would say multiple waves are suppressed at the migration. So, but we can also use this structural filtering, depending on the azimuth, illuminating from specific sectors, to be able to remove the multiples here. Okay. But we move to the next stage, and now I have been talking about separating effectively, mainly specular from diffracted energy, or applying for structural mute, also depending on the dip and azimuth. But now I want to talk about effectively natural factor characterization with VVAZ and AVAZ. So just we work orthorhombic medium. Okay, so that's just a short definition of what we understand. So it's the combination of one or two orthogonal vertical factor with isotropic or VTI in the background model. So we will consider effectively this kind, mostly this kind of structure. And of course, orthorhombic layer, it's where we have, the orthorhombic parameters that we try to solve here. So the goal with the azimuthal velocity analysis of seismic data is to extract information, of those variations here. But first of all, if we talk about velocity, we want to update the velocity model. We want to analyze the fracture. This is our goal here specifically. We want to flatten the gathers and to improve, the final image. So the context is VVAZ. We will rely on travel time variation. When we talk about AVAZ, we will talk about azimuthal analysis of seismic data. So what we want to do is to extract information, about the nature of azimuthal amplitude variation that we can observe. So that's exactly what we want to do. The two are complementary. This is not the same workflow, but the two are complementary. So I'm just presenting here, the workflow that we are applying in our solutions, from the reflectivity angle gathers, image gathers. So what we will run, is an orthorhombic, medium VVAZ inversion. So what we try to map, it's not what we try to resolve effectively, the residual move out measure along continuous full azimuth angle reflection to obtain, the effective, HTI orthorhombic model parameters. This is exactly what we want. So what we try is to map effectively the residual move out, in HTI medium. And I would say we solve mainly for three parameters in our case, the azimuth of slow velocity. This is a volume. The delta alpha, so which is the fast and slow residual move out velocities. This is what we consider as the anisotropy intensity. This is also a volume. And the slow velocity, which is effectively the velocity of minimum stress, so which is perpendicular to the factor plane. Those are effective parameters because we need to consider that the velocity depends also of the overburden. So what we will need, smooth the volume, it's maybe obvious, we will need to apply for a general Dix transformation to transform those effective parameters into local parameters into the target horizon. So which is quite important. And by then, what we will do, we will be able to create the vectors, mainly taking into account the azimuth of slow velocity and the delta alpha in our case. So it's quite interesting to start gathering, I would say, all the attributes and information that we can get. And here we see very well that, and I will show some example. If we add the wells, it's a very, we integrate effectively. From the AVAZ, so this is also an image of synthetic gathers. We work full azimuth, we keep full azimuth, we maintain full azimuth. Of course, if we are trying to minimize the residual move out in the VVAZ workflow, in the AVAZ workflow, we start from the reflection gathers after the VVAZ, but we want to apply for a real strong, I would say, automatic gather flattening to be left only with the amplitude variations that we may observe versus effectively, the azimuth. So that's the objective, here. This is, I would say, an approximation of the Chouet equation in an orthorhombic medium. So we have effectively an anisotropic gradient that will depend on the primary directions here. And we generate different volumes here, normal incident gradient, anisotropic gradient, slow velocity, and fracture density. And we can image very quickly, those are local parameters we can extract along the horizons of interest. And from mainly the two last parameters, we can get the map of anisotropy vector, which are similar to the vector displacement that we can extract from, I would say, the previous workflow VVAZ. Okay, so just a few examples here. I think it's quite interesting to get the application. Okay, so this is in the background my reflectivity gathers. We have here, the azimuth organization as an overlay. So we understand that effectively now, it's a 360. And what we can observe here, those small oscillations. So we can assume that we can make the assumptions that they are associated with the variations of travel time effectively versus azimuth, that we can to velocity variations, and we need to identify, what are those preferred orientation of anisotropy. So if we follow the workflow that I have described previously for the VVAZ here, this is, for example, what we've got here. Okay, so this is just, for example, here, what we have, this is the Eagle Ford. We have as a background, the palette color. This is the fracture density, or it could be the anisotropy intensity. Okay, so both are very similar. We can effectively make the mistakes to mix them, but in color, the background. So, and we can see the displacement vectors here, that are, and if I'm not mistaken in this example here, perpendicular to the main fractures here. So, of course, the goal would be also to map the faults here, to get a better integration, to get a more accurate ID between the relation where we observe, a high density information of the fracture and the main structural events that we have in this field. So perpendicular to the fractures here, to the main faults, right? Minimum stress, that's exactly what we are maybe looking. And in this case, it's from KOC. This is this technique has been applied in the North Howdaten field here, and we have an example here. The vectors are oriented along the minimum stress. So they are oriented, I would say, perpendicular to the fracture plane. And in our case here, what we wanted to show, a part of merging the fracture density or anisotropy, intensity with the vector displacement and the trajectory of the wells, is that the vector are, displayed based on their intensity. So, which is, of course, very nice because we can very quickly apply for a threshold on the intensity, and we are left only with what is the of highest intensity. We can see here the wells, that's the trajectory of the well, and it's perfectly aligned with the vector displacement, so perpendicular to the fracture. Here, this is another case. It's we have the full stack. That's good. And we have at that location, this is the reflectivity gathered. Okay, so we can observe those oscillations, and we have generated using a AVAZ workflow. We have generated, okay, this, I would say, fracture intensity volume. So we can compare in there. The comparison is a little bit different, okay? We want to compare, for example, the full stack, okay? This new volume, new attributes, and eventually the current skew, which is the classic attributes that we are using, that we generate from the full stack, and where we try to understand the discontinuities. Okay, but this is something at a different scales. Okay, so we do not observe here, okay, correlated information. This is a well. This is a proven example here. High fracture density. This is I would say high saturation oil well here. Okay, at the bottom here, this is the vertical well. It touched just on the side of the fracture density, okay, where we have the highest fracture density. It's a low saturation oil well. So here, another usage of this kind of information. And of course, okay, I'm talking about integration. This is what we are looking for. Okay, at the wells, we may have image log. Okay, we may deduce effectively, okay, what is the fracture log, okay, the natural fracture log. We may also define by formation what are the azimuths, okay, and we can plot that against, my seismic data. So here we have the vector displacement, we have the deep meters, and we have the well, the information from the well. So we can correlate, and this one is maybe, okay, the one we can, okay, understand the best, because it's the one maybe we see the best here on this image. So this is the azimuth of the faults here, okay, observe at the well. This is effectively here the azimuth of the vector displacement, and in the title matching the direction of maximum horizontal stress. So we are here in this case parallel to the main faults and fracture system regime here. So as a conclusion, what I wanted to come back a little bit of what we say here. Okay, so the idea is to apply for alternative imaging technologies, and let's remember that my goal is to work full azimuth. It's to take advantage of the full azimuth up to the end. I don't want to stack and to start from a stacked image where I would lose, okay, most of my information, where I will lose the diffracted energy, where I will lose, okay, the ability to analyze the variation of velocity or amplitude versus effectively the direction, the azimuth. So that's exactly what I want. I want to be able to generate from the image reflectivity gathers, and from the image, okay, directivity gathers as the seismic interpreter. I want to generate other images. I want just to access effectively this kind of data, pre-stack data, and I want to generate effectively some new images. So full field, okay, full wave field image. I want to stack, okay, all azimuth, all angles. Or maybe I want to sectorize versus the angle and azimuth. Maybe I want to apply for a combination of both. I want to generate some image that would improve, okay, my understanding of the reservoir. So maybe to create specular image, less noise, sorry, okay, a better continuity of the events. And I want to be sure I can interpret diffraction imaging the same way. This is the opposite. I want to remove the specular energy. I want to enhance the diffracted energy. I want to be able to interpret. Revitalize the legacy acquisition and optimize full azimuth acquisition. This one we saw effectively. We can generate the directivity image gathers, and we can understand better effectively the structure, okay, of my reservoir. An accurate velocity and anisotropy model. We work full azimuth. we maintain this approach, okay? So we will have, I would say, a more accurate velocity model, and that velocity model is taking care of the anisotropy model. So it's integrating the anisotropy model, okay? Exactly what I said, avoid early integration or stacking to avoid losing critical imaging information. And everything is, okay, the objective is to create deliverables, okay, with specific objective for the interpreter. So that's the goal. I want to understand the reservoir position and architecture, and I want to satisfy all the requirements of the GNG and team member. The optimizing, okay, the lab collaboration within the asset. And the last comment, it's decrease the uncertainty when simultaneously integrate more geophysical data. It could be also well data. Okay, as we saw. So I would like to thank the EAGE local chapter Kuwait for this invitation. Okay, Aspentech for having authorized this presentation, and some companies, Equino, for example, okay, and Cytel for the Volve and the Eagle 4 dataset that I'm using in this presentation. So thank you very much, and I will be pleased to answer to your question, if any question, or get your comments about effectively maybe your experience working with such a method, or when using diffraction and factor characterization. Thank you.
Thank you so much, Dr. Bruno. And kindly, if you have any questions, please just raise your hand and we'll be taking the questions starting now. Okay, please, Mr. Kalyan.
Yeah, I've got just one question, Dr. Bruno. There will be some inadequate in migration velocities, and definitely it will create some artifacts. And how do you handle those artifacts?
What do you mean by artifact? For example, with the migration first velocity, what we do is effectively, okay, we will take the velocity from the migration, and the idea is to update this velocity by running a full tomography, okay? So which means that it should minimize the artifact that you have in the final seismic image.
I mean, how many iterations you will be having?
This is something I would need to ask to the depth imaging team. Okay, providing with the, because my goal here is mainly, okay, as I introduced myself at the beginning, what I want is to be able to work from this kind of deliverables, which means the reflectivity image gathers, okay, the directivity image gathers, and to generate more product from those type of data. So I would rely, for example, on the depth imaging team. And what I would say is also just a comment is that the product I'm working with belongs to the processing team and the interpretation team, because maybe I will go back because I have some issues with the final image that I'm working with. Okay, the two image gathers. Fine.
Thanks a lot, Doctor.
Okay, thank you very much for having me here, and I hope it has been effectively informative to you.
Thank you so much for giving us from your time, and thank you all for attending. Thank you. This is Aisha Abdullah from KOC. I forgot to introduce myself in the beginning. So have a great evening and have a good day. Thank you all.
Thank you. Bye.